thank you everyone for coming today. Today we're going to be talking about the Stinson AIS, which is a Bluetooth and Wi-Fi detector, also known as a travel time sensor. So my name is Michael McGuire. I'm the VP and General Manager of Stinson ITS. And as a quick agenda, again, this is focused on travel time sensors. So we're going to start by introducing the concept. What is a travel time sensor? How is it used? What's possible with it in a more general sense. Then we'll look at the Stinson AIS. The AIS is a product I designed 7 years ago, or more than that, I guess, now when I joined Stinson. And it's come a long way since then and started to get very popular in the last year or two, especially in Ontario and Quebec. And so that was kind of the impetus to launch this webinar and start kind of showing off some of the cool stuff we're getting to work on now. And so we'll get into the sensor, talk about, what makes it unique, what are its key features. It's ultimately not that complicated, but I think it's got a very thoughtful design. And then finally, we'll get into actual projects and case studies that we've had the privilege of being part of. And then we'll finish off with a question period. So I don't have my helper today to go through and manage all the questions, so forgive me if this is a little clunky, but I'm sure we'll get through it, no problem. So if you're not familiar with Stinson ITS, it was originally a division of our parent company, Stinson. And I founded it when I joined the company in 2015 and just kind of grew it from there. And now 7 years later, we're about 14 employees. And at the beginning of 2020, kind of right as the pandemic hit, we actually broke off the division as a independent separate corporation. So we have our own little fancy office now, and we're just a team dedicated to ITS solutions. And so we're very much focused on kind of all aspects of ITS design with a focus on turnkey solutions. So we can kind of help you out with the whole package, bits and pieces, early design, product selection to full implementation and maintenance. So we've got lots of experience, and if you have a problem, we love solving traffic problems. So we're also very proud to be partnered with some of the best brands in the industry, and in particular, our Canadian brothers and sisters. There's not, a couple of years ago, there really were almost no Canadian ITS companies, and among ourselves, there's a bunch that have started to spring up, and in particular, Vermac, Livable Cities, and especially Myovision have become really key players in the market, and it's great to see kind of a Canadian presence in the ITS space. So first, we're going to look at kind of what is a travel time system, or what is a travel time sensor? What metrics can you get out of it? How is it used traditionally? How is it used more recently? And by the way, I'll mention while I'm here that if you have any questions in your toolbar, there's a small section where you can enter questions. If you can please, as they pop up, please jump in there and jot down your question. And then once we get to the question period, I'll have them all sitting there waiting, and it'll make it a lot easier. So appreciate if you do that. So what is a travel time sensor? Why should you care? Now, these things have been around for a very long time. I would guess probably 12 or 15 years on the high end, probably more like 10 or 12 years. And they've traditionally been used in very basic ways on highways, basically the travel advisory system. Highway agencies would put out sensors across an area, and then using variable message signs or VMS to advise drivers, what is the delay or how long is it going to take to get to a certain destination. And so this is what drives all the highway signs on the 400 today, 20 minutes to get the 401 or et cetera. That's all driven by sensors, software, and VMS posting it back. And that's a traditional use case that is useful, but as Google Maps and new tools come out, it's a little antiquated, and we're not seeing as much focus on that area. What we're seeing in more recent years is looking more at live congestion monitoring and origin destination studies. So we're starting to see more than just highway applications. We're seeing municipal applications where cities are putting these sensors at their intersections, and then they're able to generate travel time and average speed information from one intersection to the other. And so similar to how when you open up Google Maps, you see, your red, green, and yellow kind of congestion markers. Those are great, but it's hard and very expensive to collect that data on a large scale. And so cities opt to generate their own data and do their own congestion monitoring that's live. And that's done through these sensors typically. And so in addition to congestion monitoring, we're also seeing origin destination become popular. It's always been kind of around, but it's never really been used. And I'll speak in a moment kind of what that is and how it works. And just to touch briefly on, kind of the core concept of how a sensor works. On the left-hand side, you'll see here, essentially the whole system is based on tracking Bluetooth and Wi-Fi devices as they pass through a traffic network. And so each of these devices, when you turn on your Bluetooth or your Wi-Fi, they begin broadcasting, trying to find someone to connect to. So you turn on your Bluetooth, it's going to say, hey, I'm here, I'm ready to connect, and my unique identifier is 001A3F, et cetera. And that unique identifier is called the MAC address. And so MAC address detection and tracking is at the core of all travel time systems. And we, of course, anonymize that and everything. I'll get into that in a few minutes, but that's the core, kind of picking up MAC addresses at one sensor and then picking them up again at another sensor. Because it's always the same number, we know it's that same device that is driven between those 2 points. And I shouldn't say driven because they could be walking or on a bike, but we know that device is moved from point A to point B. So as I mentioned, the 2 key functions are travel time and origin destination. So how travel time works is just like I mentioned, you have a sensor at one point on the roadway and it has a detection radius, typically anywhere from 100 to 200 meters. And as the device passes through that detection area, we will pick up the MAC address of that device, we will encrypt it, and we will send it up to the cloud. And in the cloud, there's software gathering all this data. So a device will pass by the first detection area, and then it'll drive some set distance. It could be a few kilometers, it could be many more, but then it'll pass a second sensor. And that same MAC address from the same device will be detected again, encrypted, and sent up to the cloud. And then the cloud software does some math. It says, hey, I picked it up at this timestamp, and then I saw it again at this timestamp, so it takes 6 minutes to travel from sensor 1 to sensor 2. And because it knows the distance between those sensors, it can also calculate the average speed and say, oh, the average speed between these points for that one vehicle was on average 120 kilometers an hour. And then it'll pick up a couple thousand devices per hour and average those, and that's how you get your average travel time and your average speed every minute kind of being recalculated. And then typically from there, once it's calculated, then that travel time is taken and kind of composed into a BMS message and posted either to a permanent BMS sign or to a trailer, et cetera. That's kind of the general concept of the travel time system. Now, the other one is origin destination. As I mentioned, it's been around for a long time, but it's never been widely used, at least not in Canada from my experience, offering and supporting sensors for the last 7 years. But what it is the same thing. It's just instead of looking at segment by segment, what is the average travel time and average speed, you're actually looking for the path that a device took through your network. And so this requires more than just 2 sensors for it to be meaningful. So you need, especially on a macro level, on the right-hand side, there's a picture of kind of a stadium, an OD study that was done for a sports stadium. And so what you're doing in origin destination is tracking that unique ID as it passes by multiple sensors to understand the path they took to get to a set destination. So in this case, they said the stadium is the destination. I want to see how do people in this community travel to get to the stadium. And you can see based on the size of this bubble, there's different ways to do it. You can do percentages, but this is just a visualization, but you can see that about 30% maybe come from up here and get to the stadium from this northern part of the city. And then you can see a good chunk of them also come, maybe about 60% come from this eastern direction. And then as you funnel out further and further away from, the destination, you can kind of see the different percentages of vehicles that take one road or the other to get there. And so this can be on a macro level for stadiums. Often they can be very disruptive to traffic patterns. And so if you want to implement, specialized timing plans to kind of address those few times when the games are letting out or starting, you need to know what roads people are driving down in order to focus, in on those specific signals to make those changes. And so that's where an OD study is useful. Kind of find out what are the major routes that are taken to and from, and then focus on those for kind of the corrective action. And then on the alternative side, it doesn't have to be macro. I've spoken with a client recently that does a lot of kind of little micro studies. So they get a complaint that somebody is, diverting off of Main Street to cut through kind of a small community in order to avoid congestion. And so they set up a number of sensors kind of at that decision point where people start diverting to the right to kind of get around congestion and kind of cut a right turn. And so they set up sensors at that decision point, as well as all the potential destinations where they would go. And they just let that run for a couple of days, and then they can kind of measure, what percentage of traffic is taking a right here, how much is going through, and how much is actually ending up back on that main road after diverting to try to jump around congestion. And so you can kind of measure, you get a complaint saying people are rushing through this neighborhood. It's sometimes hard to quantify. And so by doing small origin destination studies, you can kind of quantify, is it really an issue? And then start looking into, ways to, address that, and then potentially even measure it again to see if it's been successful, whatever you're doing. Now, there's a bunch of ways to view origin destination data. There's a traditional table style. I find that difficult to read, so I prefer visualizations, especially on a map. But there's also OD circular, I think it's called circular connecting charts, and a number of software companies, offer generating OD data in this way as well. And it's just a different way to visualize, patterns from one place to another. Now, I mentioned tracking your cell phone, and that never sounds anything but creepy. So of course, privacy concerns, get raised right away. And so I wanted to address that here. And really, I've been kind of surprised in the industry. There's been no standardization around, what procedures should be put in place. But the general practice seems to be exactly what we do, which is anonymizing data at the edge. So the way our device works is it's sniffing the air around it, again, 100 to 200 meters. And when it picks up a device, it pulls in, it reads its MAC address, then it applies what's called a hashing technique to it. And it's just a way to encrypt the data into a random string of numbers that can't get decrypted back to this MAC address. And so it's just a way of hiding, because this actual MAC address is sitting on someone's phone. If you were to go into your settings, you can see what that MAC is. So the idea is to just scramble this number into something that's, consistently the same number, but not, decryptable back to the original number. And so, we encrypt and hash at the edge, and then this output number is what gets sent to the cloud for matching at other sensors. And that seems to be the standard in the industry, although there is no specific requirements that I've seen in North America. So that's it for kind of the concept of travel time. Again, travel time and OD. Congestion monitoring is interesting. I'll show you a little bit about a very cool project we're doing with the MTO, where they're using sensors in a very dense fashion for congestion monitoring. And it's the first that I know of in North America of that. And so you may find that interesting. But first, we're going to get into some details on the AIS sensor itself, and how does it work, and what are some of its key features. So this is the AIS. To be honest, I don't even remember what the AIS stands for anymore. I think it was Advanced Intelligence Sensor or something like that, but we kind of made it up on the spot 7 years ago and kind of have never revisited it. So so this is starting to get more popular. We're going to start exporting it. Maybe we'll look at rebranding, but yeah, that's what it is. And we pronounce it the AIS. And it comes in a few different flavors. On the next page, I'll show you kind of what version 1 looked like. That was a lot more kind of ghetto than what it is now. But after all these years, it's kind of turned into a very professionalized, well-engineered device that's kind of gone through all the paces and is quite reliable. So we're very happy with it. But in its current kind of generation, it comes in 2 form factors. The one on the left is called the shelf mount. This is intended for installation in a PVMS trailers. So if you're doing a work zone travel time system, typically the sensors go in the actual PVMS trailers themselves. And so you can kind of do point-to-point travel times on each side of a work zone. And this device is also alternatively intended to go into traffic cabinets. So the big difference is that it's not weatherproof. It has to be in an enclosure. So it goes into either a trailer or into a traffic signal, and then an antenna is mounted on the top of the enclosure, and that antenna is outside of the metal box it's in so that it can detect the vehicles, or sorry, the devices as they come and go. So fairly straightforward. There's two antenna connectors, one for Wi-Fi, one for Bluetooth, and then the device is powered over Ethernet. So we have a wide input range of 9 to 32 volts. We build our own really rugged PoEs, but we can also use cabinet power. So if you have 24 volts in your cabinet or a solar system or anything, we can tap into that and use that to power the device. So just one cable will run it. And alternatively, the other model we have is what we call the AIS-P, or the pole mount version of it. And it's the same thing, it's just the guts put into an IP67 enclosure. And the big difference is that it goes outside, so it's weatherproof, but more importantly, it uses larger antennas. So when we utilize the shelf mount, we often use kind of a puck antenna, which is a 3 dB, and that will get us that 100-meter range. But we built this unit to be more highway focused. So 100 meters doesn't get you very far on the highway, and we're learning that with this MTO project. So it's worked out really well for us. We've never done a ton of highway work where this was needed, but it's starting to come up a lot now. And so these larger antennas are 5 dB instead of 3, and so we get a lot more range out of them. And because they're typically up on a pole, you also get better line of sight to the vehicles themselves. And so that also helps with reception and range. And so same concept, a single wire Ethernet cable up to this box will give it power and communication, and run back to the cabinet or wherever you're going from here. So some of the key features of this that maybe aren't unique, I should say, but I think are thoughtful features that for whatever reason have not been widely adopted in the industry. So I've highlighted them here in red. And the first is Wi-Fi and Bluetooth detection. So it's not complicated to do both at the same time. It's almost the exact same function, but for whatever reason over the years, it seems like manufacturers choose one or the other. And I never quite understood it, but we started supporting Wi-Fi very early on because it just made sense. It's just more data. And one thing to mention is that people think you're picking up every device, so you're tracking every car, so you can do counts and you can do volume studies and all that. That's not the case with these devices. We haven't done a validation study in a few years, but typically with these sensors, they're very comparable. You're capturing only about 10 to 15% of the actual vehicles driving down the road. So it's not useful for volume because that penetration rate varies as well. So you can't just extrapolate that to say, oh, it's 15, so it must be 10,000 cars. But it's statistically significant enough that you can extrapolate the traffic conditions. So even though you're only getting 50% of traffic, that 15% has to go through the same traffic conditions as the remaining 85. And so you can extrapolate out based on what they experienced as the general conditions for the roadway. So just thought I'd mention that in case you're having some ideas of how else this might be used. So we support both Bluetooth and Wi-Fi and Bluetooth low energy. And in fact, low energy is the biggest collector of data. So by far the highest number of detections we get is Bluetooth LE, low energy, and Wi-Fi. And then just normal Bluetooth still gives us some data, but it's the least out of the three that we support. And the second one, I think this is maybe unique. I imagine people will slowly start moving over, but we come from traffic, and we all are familiar with NTCIP standards, and interoperability is a big part of that, and not being proprietary, not siloing everything. And so when we built this, it was very important to us to be interoperable. And so we have a open protocol or published API so that anyone, either a private user that wants to do their own offline data crunching, or any third-party software that wants to ingest raw data from the sensor and doing their own travel time calculations, they're able to do that. And so early on when we launched this product, we partnered with Transnomus and their ITS Central platform because they integrated our protocol. But our hope was to kind of push the industry and say, hey, let's separate the software from the device. And I can't say we've been successful, but that's been our strategy. Typically, most travel time sensor providers have proprietary sensor, proprietary software, and the sensor only talks to their software. And it's just it's a way to lock you in and force you to always go back to them for the software. So once you're in for 30, 40, 50 sensors, you really cannot change vendors. And so the idea here is just keep it agnostic. If you want to switch vendors, you have the flexibility to do so. The biggest challenge in the industry right now is that there's only a few ATMS providers that will actually ingest raw travel time data. And I'll get into it later, but currently the two we know we're supported by is Transnomus's ITS Central and Genetec Security Center and their home mobility platform. And another key feature is passive PoE. I mentioned that just makes installation and a breeze, a single cable and a very common cable. Now they're also very low power, give or take about 3 watts consumption, so very solar friendly. They also have the option now of built-in LTE. So if you want something that's just going to plug it in and start spitting data to the cloud, we can give you very easy turnkey solutions. That's especially useful in temporary study conditions. And then finally, just a robust device. It is NEMA TS2 compliant, but we've gone and tested it even beyond those limits that it can handle extreme cold and extreme hot temperatures. And we've had this out for the last 7 years and kind of gone through the gamut of little issues along the way, but the last 3-4 years, it's really, we finalized the design and it's been working very well for us. Oh, yes, so here, this is version 1. So this is what I came up with. One of the first projects, 6 months when I was at the company, was kind of putting this together. And so didn't look like much, but in reality, the design has only changed, by, different, I think we didn't have Wi-Fi at the time, so we've added Wi-Fi and LTE, some stuff like that. But the guts are not that far off from what this original one was. But this is the first iteration. And then I think after that, we shortly came, I think 2017, I came up with this one. And then maybe 2018, 2019, we started building this as our new standard shelf mount. So just speaking a bit more about the open protocol, if you have an interest in this, we are very willing to share the protocol documentation, kind of how it works. On the right is a view of kind of what a raw data output would look like. This is also how our data archives or logging looks like. We've partnered with Ryerson and some other universities that want to do travel time studies, but in an offline sense, and they want to process the data themselves, do their own device matching and analytics. And so they can kind of take a log file that has, thousands of these detections and do their own device matching. So I won't get into the nitty gritty, but in general, the operation you can see here is WFF, WFI, BTI, BLF. So that's basically saying Wi-Fi initial. So the first time I've seen this MAC address at this timestamp, and then WFF is I saw this MAC address for the final time. This is when I first saw it. This is when I last saw it. So you can kind of gain some insights for how long a device has dwelled within its detection zone. Things like intersection delay and other metrics. Even people have used these sensors in commercial environments where you wanted to detect how long people are waiting in line at, say, the airport, or how long somebody stands in front of your advertising sign at the mall. These sensors are used there to kind of try to capture data on how long you're standing in front of something or how long you're waiting. So this kind of just tells you when it first saw the device, when it last saw the device, how long that period was, etc. And it tells you the type of device it detected. So as far as configuring the device, it's very straightforward. It's all done through a web interface. So there's a web server that's hosted on the device. So either remotely or locally, you jump on and you're able to kind of configure everything in there. There's really not a whole lot to configure. This is more used as a diagnostic tool. That the main thing you're going to set for these sensors is the IP address. And often these are deployed with LTE modems, so the default IP even stays the same. It's more on the modem where you're doing your network config. But you can access your network configuration, device configuration. We've also used this for some custom applications interfacing with loop stations and others. So that's when you might get into that configuration page, but generally nothing there you need to touch. You can see that the application is running. You know, if for some reason you're not getting data, you can come in here and make sure that the process, that is the kind of the detection process for the sensor, is actually running. If it's not, you can restart it here. If you want to restart the whole device, you can also do that here. So it's just a good place to go to diagnose any issues you're having with your device. And so in addition, you can also view data archives and live data. So that's what this next slide is showing. So on the left-hand side, if you were to get down to data archives, the device has an SD card built into it. On the front of the shelf mount, you can get to it very easily. In the slot with the pull mount, you have to open it up to pull it out. And what that archive includes is kind of, depending on how, on a highway environment, you're getting about 1 to 2 years worth of backup data. So every day, 24 hours of basically this data, just like you see it, is in an archive file and is saved as a separate entry into that SD card. So if you're on a smaller road, it's more like probably 3, 4, 5 years worth of backup data, but it's just a record in case for some reason the cellular connection goes down. Once it comes back up, you can still, you know, pull that historical data and re-merge it into your databases. And so it's, you know, one for self-healing kind of data side, as well as if you're going to do an offline application, like I was mentioning with Ryerson, they can just go in there, do offline studies with no connectivity, and then just pull the archives after the fact to do their own data matching. And then finally, you can also go to the TCP live data page, and this just shows you detection spitting out in real time. So if you're worried somebody, you know, you're not getting your data, you can jump on here and make sure Bluetooth is spitting out. Yep, okay, we're good. Wi-Fi spitting out. Okay, both of those are running good. And you know that detections are happening and maybe the problem's somewhere else. Or maybe you're just getting Bluetooth and then maybe you want to look at the Wi-Fi and why that's not working. So just a good tool to verify data's coming in and you're good to go. And this is how it's set up. Basically, an antenna plugs into the antenna ports and then that single Ethernet cord. So this is a more the off the shelf. This is not the one that we supply anymore, but an off the shelf PoE. And you plug this into your laptop to do your initial configuration, and then you're off to the races. If this was in a cabinet, the dividing line would kind of be at this point where the antenna would sit on top of the cabinet and these guts would sit inside. And then obviously that Ethernet would plug into your network, your modem, or whatever, you know, connectivity you have in the cabinet. If this was a pole mount, then the dividing line would be at this Ethernet. So the sensor and its built-in antennas would be up on the pole, and then just the power adapter would be inside the cabinet. So just to look at some of our key partners, both clients and software. As I mentioned, you know, our 2 software integrations at this point are through Transnomus's ITS Central platform and Genetec's travel time engine. And some key clients, the biggest by far is the MTO. We have that multiple hundred sensors going out right now, essentially, and so we'll take a peek at that a little bit later. Durham Region is one of those municipal clients. We've worked with them for the past 3 or 4 years. They have about 60 sensors out at all the different intersections doing exactly that congestion monitoring that I mentioned earlier. And so Montreal and Toronto are also doing the same thing. Montreal's got about 40 of them. Toronto's just, I think, we've got 5 or 6. And then MTQ, same thing as MTO, is doing highway monitoring. And we also do travel time across the Peace Bridge down in Niagara. So these is, you know, we've done a bunch more, but they've been very focused on our own work zones, long-term Eglinton LRT, Finch LRT, really long smart work zones. We will use the sensor for our own purposes. But as far as permanent deployments, these are by far the largest clients we've had. So this is the look at the 2 platforms. This is, you know, ITS Central on the left. It's a cloud-based web interface. And then Genetec does have a cloud element possible, but it's traditionally been a client-based, like software on your PC to run it. And so it's, you know, if you're not familiar with Genetec, a lot of municipalities use this as their video management platform. And you might not be aware, but they launched a few years ago many different ATMS-focused modules, one of them being a travel time engine and a VMS, or what they call DMS, digital message sign control module. And so if you have Genetec, you could add those modules to it at a very reasonable price and begin to be able to support travel time sensors. Otherwise, if we're starting fresh with someone, we'll often utilize ITS Central because it's very simple and easy. You know, it can be offered in a SaaS model where we have everything hosted in the cloud and put the sensors out there, and we can configure everything from our desk, and it starts working. Whereas you don't have to start installing software or servers in your office, etc. But there's value in both of them. Just as an FYI, it seems most of our deployments in Ontario are ITS Central based, whereas in Quebec, Genetec is very dominant, and all our deployments in Montreal and MTQ utilize Genetec Security Center. Okay, perfect. So that's the sensor, fairly straightforward, but I think well designed, and yeah, very pleased to start to have some success with it. And so as far as projects, I mentioned the big MTO project. This is a real exciting one for us. It's been a bit overwhelming. We've never built 200, you know, in this case, we have to build kind of AC power boxes, solar power boxes, and sensors. So we have like 500 boxes in the back right now, just being manufactured the last few months. And it's been kind of a fun, kind of crazy run here. And so this is the MTO released a contract in, I think, December or January of this year. And we partnered with Black & McDonald and Transnomus to offer a travel time system. So this is a supply, install, operate, and maintain for 5 years with an optional 2 years after that. So we're providing the sensors, Transnomus is providing the software, and Black & McDonald is providing the installation and maintenance of the system. And so it's 230 sensors, plus or minus, but approximately that many. And they're spread out across just central region. So it might not look like 230 dots, but these icons are very densely placed. And this is not kind of the density needed for travel time. You can space them out a lot more and still get good travel time. But if you're familiar with David Suey, this was kind of his brainchild at MTO to start looking at different ways to use travel time data. And traditionally, monitoring congestion for highway agencies was done using side-fire radar sensors. So they're looking at speed and volume and occupancy and trying to estimate travel conditions based on that. And the challenge with those sensors is that they only look at a sliver of the roadway. And so you have a sensor here, you have another one 1 kilometer or 2 kilometers down the road, and you can kind of tell what the average speed is there and what it is here. But if there's a big accident in the middle, the second sensor is going to tell you that there's no traffic, it's flying fast, it's no problem. So the big thing is you can't see what's happening in between those sensors. Whereas with travel time sensors, you only capture a data point when a device travels along that entire segment or that entire path and hits the second sensor. So by collecting those data points, you can actually tell what were the conditions in between each sensor, and that allows you to just gain a lot more kind of coverage of your roadway and, you know, monitoring what exactly is happening. And so those radar sensors still have a ton of value and they're not going away, but give or take, the MTO strategy was to eliminate 1/3 of their count stations and opt to go with a dense travel time sensor network. And so I believe this is the largest network in North America. And at the very least, it is the only one I'm aware of that's doing this very congestion focused monitoring approach. And so this is in the process of being deployed right now. I think we're at about 50 units or so and should be up and running by maybe Q1, Q2 of next year. So really exciting project, and it's been a pleasure to work with the MTO and Black & Mac and Transnomus on this one. Oh, and sorry, I should mention while I got you here, due to the contract requirements, we had to use a different enclosure. They called for non-metallic. So this is, you know, what the unit ended up looking like. So it's basically the guts of our sensor with a LTE modem, in this case, a micro hard modem, put together in the same box. And so it's really is plug and play. Everything's pre-configured. You just give it power and it just starts sending data to the cloud. So easy peasy. And this is the setup we often use for temporary studies, so that you don't got to worry about configuring anything. You just got to give it power one way or the other and mount it on a pole. So another project I was going to look at is one in Quebec. And so in Quebec, we've partnered with Innovation MIA as our distributor. And they've started, as I mentioned earlier, having a lot of success in the Montreal area as well as with the province. And one of the exciting projects they deployed a few years ago was this big tunnel project. I think it's been about 2 years now it's been up and running, but there's a tunnel underneath the river here that was being renovated and would often have to have lane reductions or complete closures. And so they wanted to really manage expectations as people approach the tunnel. And so they deployed a network of Bluetooth sensors or travel time sensors to kind of measure congestion and travel time, and then provide that to the public at key areas as they approach the region, so they know if there's crazy delays, don't try to go to the tunnel, just keep moving, find another way across the river. And so they have 25 travel time sensors, 12 VMS hybrid signs across this whole area. And so on the bottom right, you can kind of see the setup they have. This device on the top is a smart micro radar sensor, so they're doing counts as well for volume. But in the box here, you can see a little antenna on top. They're utilizing the shelf mount unit to capture data on these highways. We could use, I know some of them use the outdoor sensor in wider areas, but if you're not on a very large highway, the shelf mount is no problem. 100 meters is plenty. But this is a custom structure that MAA developed, and these are kind of spread out across the whole region. And this is Transnomus' software, so this is what ITS Central looks like, just branded for MIA. And this is an idea of what the signs look like. So they got these static signs with these variable message sign inserts, and they have those strategically placed throughout the region to kind of broadcast travel time information to the public. And that's it. One final slide here I was going to show you. So new trends. As I mentioned, VMS signs are a big part of travel time systems. And so I just wanted to kind of put a plug in for an interesting project we've been working on with York Region. So they've been looking at high resolution, full color PVMS, and they're actually deploying it next week. So it's going to be cool. And one of the key applications they were looking at is deploying travel time messaging with color context. So often you'll see a sign that says, hey, it takes 20 minutes to get to 401, but you have no idea if that's horrible travel time or if it's great travel time. So by putting in colors, red, yellow, and green, you can kind of gauge if this is a reasonable travel time or if you should consider diverting. And so this is the first time I've seen this deployed. I know the MTO signs are full color, but they don't seem to utilize kind of color context at all. So very excited to see this go out, and keep an eye on our LinkedIn. We'll be posting some photos next week. And that's it. So thank you everyone for coming today.